This video will show you how to interpret a multiple linear regression model created in SPSS. We'll also check that the assumptions of multiple linear regression are satisfied. We will continue the example presented in video 1 and 2. In video 2, we concluded that only weight, age, gender, 1 mile walk time and heart rate were significant predictors of VO2 max. So I've created a linear regression model with only these predictors to make the output clear. All settings and plots are as in video 1. We get the following output. The model summary and ANOVA were discussed in video 1 for the full model, and the same arguments apply here. We will again use the coefficients table to get the final equation for our model. We have VO2 equals 8.024 plus 0.008 times weight minus 0.027 times age plus 0.926 times gender minus 0.215 times time and minus 0.013 times heart rate. We could interpret the constant term as the VO2 max for an individual who had values of 0 for all the other variables, but in this case it does not really make sense to interpret the constant in this way. We can interpret the other coefficients as the change in VO2 max for a unit change in that variable when all the other variables are fixed. For example, the coefficient for gender is 0.926, so a male will have a VO2 max that is 0.926 higher than a female of the same age and weight with the same 1 mile walk time and heart rate. The sign of the coefficients is also important. Since the coefficient for weight is positive, an increase in weight corresponds to an increase in VO2 max. The coefficients for age, 1 mile walk time and heart rate are all negative, so as each of these increases, VO2 max decreases. If we know an individual's weight, age, gender, 1 mile walk time and heart rate, we can use the model to make a prediction of their VO2 max. For example, consider a 30-year-old female weighing 160 pounds with a walk time of 18 minutes and a heart rate of 169. We calculate the VO2 max by substituting each value into the equation to get a VO2 max of 2.427. Note that it only makes sense to make predictions for individuals that fall within our data range. For example, we only collected data for people aged between 20 and 40. The relationship between age and VO2 max may be different outside this range. We should only use our equation to make predictions for the original population from which our sample was taken. Now we will look at the 4 assumptions of linear regression. They are that the relationship between the independent variable and the dependent variable is linear. The values of the residuals are independent. The variance of the residuals is a constant, and the values of the residuals are normally distributed. We actually checked the first assumption before we made our model using a matrix scatter plot to look at the relationship between each variable. It is important to check this assumption as SPSS can find a linear regression model for any set of data, but this does not mean that the model is a good fit. Another model may be more appropriate, such as a quadratic equation. The second assumption should have been checked in the design of the study or experiment. It means that we cannot use linear regression in situations where the residuals are related. This is the same as the observations not being independent. For example, we cannot use linear regression to model changes in one individual over time, as the observations, and therefore the residuals, are related. We also want the residuals to have constant variance. This is called homoscedasticity. To test this, we'll use the scatter plot we created earlier with the standardized predicted y values on the x-axis and the standardized residuals on the y-axis. What we are looking for is that as the predicted values increase, the variance of the residuals stays constant. That is, the residuals can be contained within the 2 straight red lines. Apart from some outliers, this assumption seems to be satisfied. Linear regression is robust and will still get reliable results if this assumption is violated. If we see extreme patterns or funneling of the residuals, this is called heteroscedasticity. The last assumption is that the residuals are normally distributed. We can test this assumption using the histogram of the residuals created earlier. We want to check whether the residuals follow the shape of the normal distribution curve. A violation of this assumption will only significantly affect the model if the residuals are very far from a normal distribution, and we'll get biased estimates for the coefficients. Our histogram seems to roughly follow a normal curve, so we can conclude that all the assumptions are satisfied for this linear regression model. If the data does not satisfy the assumptions of linear regression, you can try transforming the data in some way, such as a log transform, so that the assumptions are satisfied. In summary, this video has looked at interpreting the coefficients of a regression equation and using a regression equation to make predictions. In particular, you should be aware of any limitations in the predictions you can make. We have also checked that the assumptions of linear regression are satisfied and shown the techniques for checking these assumptions.